All right, we're back. We're on page 118. We are talking about two-dimensional vectors, kind of an introduction to them, like what are they, what can they do for us? We don't really know what they can do for us yet, but we definitely know what they are. They are things that have magnitude and direction. So is that useful? I don't know, maybe not yet. But to find the magnitude, we found it's really just finding the distance between 2 points, the initial point and the terminal point. And so we can use the Pythagorean theorem, we can use the distance formula, you can just basically look at it and be like, that's a triangle. However you want to do that. So in this problem, we're going to find the magnitude of each of the vectors. We're going to confirm on the calculator. I'm also going to show you how you can do a little bit of this stuff on GeoGebra. It's not really the most user-friendly experience. But anyway, so the vector v, remember, you can name a vector using its initial and terminal point. So if for example, this had been A and this had been B, we could have said that the vector was from A to B, starting at A, ending at B, but we just named it vector V for convenience, which you do a lot of. It's more convenient to have a single variable naming your vector than it is to have to refer to the start and end point, especially considering once you've used the start and end point to peel off the directions, like what are you supposed to do? Are you moving left or right, and by how much? Are you moving up and down, by how much? Once you peel off that information, the initial and terminal point, like the specific initial and terminal point, don't matter anymore. You can then have whatever initial point you want. Follow the directions, you'll get whatever terminal point you need. So let's move over to GeoGebra and I'll show you kind of a little what I mean by that. So I'm on GeoGebra Classic. Go to geogebra.org and choose Classic. It gives you all of the options that we're going to need to do this. I'm going to plot the points. So I'm going to call it, well, I'm not going to call it anything. I'm going to 2, 6. And then, so you can't see that because it's not actually on the screen right now. And then -3, 8, which also I think you won't be able to see. Let me zoom out. Okay, so now we can see some points. I can make a vector in 2 ways. One of them, so 2 different ways. First, I can here just click vector. I need to give it a starting point and an ending point. So I want to start at A and end at B. And you can see that GeoGebra creates the vector. It names it. So it named it U because it always starts naming vectors at U, and then it V, W, and like keeps going. And it shows the vector is, here's your initial point, here's your terminal point. And if you look on the side here, it tells you this. Now, this is not the notation that we use. We're going to use more of an ordered pair. But that first component, so this looks like a matrix, right? 2 rows, 1 column matrix, 2 by 1. 2 rows, 1 column. Yeah. Row by column. Yeah. I don't know why I'm having trouble with that. The first element here is -5. That -5 is telling you how far to move in the left-right direction, right? Horizontally. So move 5 to the left. And then the next component is saying +2, so move 2 up. So starting at the point 2, 6, move 5 to the left. So 2 minus 5 is -3. Then move 2 up, 6 plus 2 is 8. So that gives us the vector. So the vector, the set of information is 5 to the left, or -5, and 2 up, or 2. So another way I could have made this vector is I could have started typing just vector. Right? And so you can see here, there's a couple of options. One is vector where you just give it a point, and then vector where you give a start and an end point. I'm gonna use that one. So vector, my starting point is A and my ending point is B. And I'm gonna press enter and see what happens. So I don't see the vector V. I was expecting to see it, so I don't really know what's going on there. Oh, V is it's up here. So, okay, so I accidentally moved this, and now how do I get it back? Okay, there we go. But that kind of illustrates the point. Watch what happens as I move this around kind of foolishly, right? So watch the coordinates of A and B, but also watch vector U, right, and V. The vectors aren't changing. They have the same magnitude and direction, right? So there's nothing going on there. But the points A and B are obviously moving. I'm going to try to put them back where they belong. All right, so now you can do all kinds of weird things if you want to in GeoGebra, right? So I can do a vector, and I want the initial point to be 0, 0. And let's say that I want the terminal point to just be, I don't know. I can actually use, I think I can, oh, no, maybe not. I'm going to do 0, 0 plus U. So I'm adding the vector u to 0, 0. I'm saying start at 0, 0, and then apply the vector u. And you can see this. And you can see it's the same vector, same magnitude, same direction, same vector, right? Two different names, same exact vector. We can put a point. So this is a little more interesting. I can just put a random point. And now I'm going to do the same thing. I'm going to say vector, start at point C, and then do C plus the vector V. Okay, so now I can move C around, but you can see the directions are just embedded in the vector. Wherever C is, you have to move 5 to the left, you have to move 2 up. So this is one of the ways GeoGebra plays around with these. Not really the point, but I think that the more you can play around with them, the better. For example, I can actually move B. And when I move B, you can see all of the vectors, because all the vectors are based on the relationship between points A and B. All of the vectors change. So even though I'm not really doing anything at point C, I'm changing the directions, right? So now I can move C. The vector maintains its direction and it maintains its magnitude. This is why I think it'd be very annoying to carry a vector around, right? Like you're carrying this vector, there's nothing you can do. You can't change its direction, you can't change its length, nothing you can do. All right, but keep in mind, right? So we, I don't think I'm gonna be able to get back. Maybe, I don't know. I'm gonna go back to the notes and go back to the originals. Let's see. So the calculator, because we're just doing a technology thing here. The calculator can find the magnitude of this. I mean, we can find the magnitude also, right? So our delta x. So if we think of V as a set of directions, and those directions, so I'm going to use, these are called chevrons. It's like a greater than and then a less than symbol, a less than and then a greater than. So a chevron as like delta x and then delta y, where the order really, really matters. You have to start and end, right? So if you start at 2 and end at -3, you went 5 to the left. So I'm going to say that the vector V contains the information, move 5 to the left. And then if you start at 6 and end at 8, you have to go 2 up, right? I'm going to say that's the vector V. Now it's important to have that notation because the calculator needs that. And the calculator also will take this a slightly different way. So the magnitude of V should be the square root of 25 plus 4. So the magnitude of V is going to be the square root of 29. All right, let's get our calculator to give us this answer, and then we'll speed through the other 2 examples here. Well, maybe, who knows? I never know what I'm going to go fast on and so on. All right, so norm, menu 7C. And then, nope, menu 7, 7. Sorry, hold on, I got this. Menu 7, 7, enter, gives you the norm. The norm is just another word for magnitude, but now I need to put in the vector. So the vector, what we're going to do is control and then open parentheses, and you get brackets, right? And this is how you're going to enter your vector. It's essentially a matrix. Do -5, then comma, and then 2, and press enter, and you get radical 29. A sort of interesting thing that you can do is you can have the calculator just do the calculation for you. Like we can put in our terminal point, -3, 8, minus our initial point. So I'm putting these in vectors. Like I am treating each point as a vector, which is something you do all the time. I'm gonna press enter and see what I get. I get -5, 2, and then I can just find the norm of that. Menu 7, 7, enter of this, and I get this. But I could have just done the whole thing straight through, right? So I'm actually gonna do problem B right now. I'm gonna say menu 7, 7, enter. The terminal point where I'm going to end up is 4, 8, minus the initial point is -3, 5. So why am I doing the terminal point minus the initial point? Well, I need to know what the change in x is, right? So if I end up at 4 and I started at -3, the change is 4 minus -3. If I started at 5 and I end up, wait, I think I did that backwards. I don't really know. If I end up at 4 and I started at -3, I must have gone 7 to the right. If I end at 8 and I started at 5, I must have gone 3 up, right? So I have to do terminal minus initial to get the correct sign on the change. So I'm going to press enter here, and you can see we get radical 58 I'm going to go back to the notes and show you how I would write this, I think. How I think I would write it, I guess. Okay, so here I'm going to say that the vector b is the set of information, right? So I start at -3 and I end at 4, so it's got to be 7 to the right. I start at 5 and I end at 8, so it's got to be 3 up. So this is the vector b, and then I am finding the magnitude of b, or the norm of b, or the length of b. 49 plus 9, so there's your radical 58. Okay, let's try this one. So R is the set of information. So if I start at 8 and I end at -3, then I went -3 minus 8, -11. So I'll do this, -3 minus 8. And then if I start at 2 and end at 7, I must have gone 7 minus 2, which is 5 units. So 7 minus 2. So you're always just doing the terminal point minus the initial point to figure out like what set of information you're dealing with. So the vector R is really just the set of information. Go 11 to the left, go 5 up. And then the magnitude, norm, or length of R is the square root of 121 plus 25. So the square root of 146, which the calculator could confirm for us. So maybe I'll switch back to the calculator just to confirm. And then maybe, I don't know, this, all right, so let's do this. The norm of -3, 7 minus 8, 2. Radical 146. Got it. Okay, so we can do these things. You need to know how to do things on the calculator, like no question about it. So let's like just do the rest of this page, because I think it's not really that long. Is it that long? Yeah, it's not really that long. All right, by definition, two vectors are equal if and only if is a big deal. Two vectors are equal if and only if they have the same magnitude and direction. So you might think you're looking at a lot of vectors, but in fact, you might be looking at the same vector multiple times, right? If a vector says move 1 to the right and 2 up, every time you see that vector, it's actually the same vector. It can be used all over the place. They're, I don't know, omnipresent or whatever. So this picture has a lot of vectors, but fewer than you think, because a lot of them are actually the same. So let's go hunting. I'm just gonna change the color that I'm using and highlight them, I think. So the vector U, let's start. Well, let's go in order. So A, here's a vector A. So it's, you can kind of visually see these, I think. A and E are definitely the same. I don't see any others that appear to be the same length and the same direction. So I'm going to say here that vector A equals vector E. A equals E. They have the same magnitude, they're the same length, and they're both pointed like down and to the right, I guess. Let's change up the color. So I guess B, if I can find it. Which, D, is there a B? B, found it. Here's B. So I want any vector that has the same magnitude, same direction. So you can just like eyeball it for the magnitude, I think. Like H is definitely going the same general direction. And then I think it's easy enough to see that they're the same. So B equals H, vector B equals vector H. And then switch, so C, here we go. So what else? CI looks good. F looks the same. This is interesting. There's a lot of them. K looks the same. Okay, so these all look the same. So C, F, I, K, I don't know, C equals F equals I equals K. Okay, so that one, there were a lot. So actually, so far, I've only actually highlighted 3 vectors. Like, you can't really get your head around that. But like, A and E are the same vector. That's one vector. It's just showing up twice. So switch colors. And then what am I up to? D, if I could find it. D. It's here. You can see V is going to be the same. So are there any others that look like that? No. Highlighting this is actually like way easier than usually. like in person, it's kind of like a task. And there's no like convenient way to just like check off that you've already dealt with a vector. New color. So D, E, F. Is there a G? There is G. G and U are definitely the same. So G, U. G equal to U. And so, I mean, when you're doing this is like, it's like a dumb game. I mean, you could give this to a kindergartner and they would be able to do it. They may not understand it, but also you might not understand yet exactly what's happening. It's nice though, because it gives you like a familiarity. So like at the end of this, we'll see there's 1, 2, 3, 4, 5. So far there's 5 unique vectors. It looks like J and Z go together. And then W looks like it's all by itself. J equals Z, and then W, all by itself, I think. I'm gonna highlight it anyway, so it's not like that ostracized. W, all alone. Okay, so 2 vectors are equal if and only if they have the same magnitude and the same direction. So you can see there aren't as many as you would think. There's like half as many, maybe a little less than half. So how do you determine if they have the same magnitude? I mean, I think what we did was we just kind of like looked. Just look. But a better answer is like, you can actually just compare delta x's and delta y's. Like you don't need to find the length. You just need to know if they have the same delta x and delta y. So for example, here, for this one, like 4 and -3. So you go over here and you're like, well, 4 and -3, got to be the same magnitude. So there's other vectors. I believe that B has the same magnitude because it's -4 and 3, 4 to the left and then 3 up. It's not the same vector because it's pointing in a different direction. So that's a little harder. So for in this particular case, the direction, we just like looked at the arrows. And that's totally fine. I mean, like, we don't need to do more. These aren't trick questions. But we want to get better at that because like arrows aren't always going to be convenient. And also, what if there's a vector that's like, I don't know, 50 to the right and 49 up, and another one that's 50 to the right and 49.1 up. You're not going to be able to eyeball that. Like, there's no way. So we need something better. But for now, I think it's okay. Maybe you talked about slope. I don't know. A lot going on there. But anyway, I'm going to stop this here. I know it's kind of a lot, but start thinking about vectors as much as you can. They're really not that bad. I'll be back in the next video, and we will do more with them. See you there.